today's class, we will discuss about control valve. In last class, we discussed about final control element. Actually, final control element consists of two distinct parts. One is the actuator, the sensing system, and control valve. The second part is the control valve. In last class, we discussed about the sensing systems, that is the actuator, different types of actuator, their principle of operation, etc. And in today's class, we will discuss about the second part of the final control element, that is the control valve. So, control valve again consists of two parts, that is the plug and stem. Just consider the above part of this portion. There is the sensing system actuator. So after getting the signal, this is basically for pneumatic actuator. So after getting signal to the diaphragm, the stem will move accordingly, and this is the plug and this is called seat. As I discussed in last class also, that this is the plug and seat arrangement, where the plug, depending on the stem movement, the plug will close or open the seat area, so that the fluid flow path is like this. So accordingly, it will allow the fluid flow through this valve. So this is the function of control valve. So control valve consists of two arrangements, that is this plug and the stem. So depending on the signal reaches from the controller to the final control element, that is to the actuator, the stem will move accordingly, and then the plug will position to the seat area again accordingly. So based on action, number of plugs and flow characteristics, the control valves can be defined. Control valves are available in different types and shapes. They can be classified based on action, number of plugs and flow characteristic. This is the control valve air failure to open type or air to close type, and air failure to close type or air to open type, that I mentioned in our last class also for pneumatic actuator, that air failure to open type or air to close type, or and another is air failure to close type or air to open type. I think I should not repeat this once again. Next is structure wise classification. Depending on several conditions of the pipelines, a large variety of control valve body has been designed. All these designs are depending on the requirement. For several conditions of pipelines, the control valve body has been designed with different structures. So they can be classified broadly as sliding stem or globe body. That is most commonly available type of control valve. So far we have shown the figures. All are sliding stem or globe body type, where the stem should be slided within the through the seat area. So this is the sliding stem type. Rotating stem is screw type structure, where it rotates like a screw and fits to the seat area, the plug fits to the seat area. And specialized body, these are for special operations in order to handle special type of slurry or special type of operations. So special structured body, maybe butterfly valve, other ball valve, these are special type valve bodies. Sliding stem or globe body has straight or angle configuration, which we have seen earlier also. So all have straight movement or angle movement of the stem, so that the plug can fit to the seat area directly. Rotating stem rotates about an axis, and the plug of the control valve also rotates about that axis, screw-like structure, in order to open or close the valve. A specialized valve body is a special structured body designed in order to handle special slurry of very slow flow rate or very high pressure, WAC type, gate valve type. These are specialized valve body. Next is stream of control action. What is stream of control action? The parts of the control valve which are in contact with the process fluid. Just note the point that the control valve consists of stem, plug and seat area. So the parts of the control valve which are in contact with the process fluid are together called stream of control action. Control valve, plug, stem and seat and cage. That means the lower portion of the final control element together forms the stream of control action. Control valves can also be characterized as a number of plugs in terms of number of plugs present, single seated valve, double seated valve. In last class I have mentioned that single seated there is a typical disadvantage of single seated valve, and other type of valves are available. This is how many number of plugs are present in the control valve. So depending on the number of plugs, the valve can be categorized as single seated valve and double seated valve. Only these two types are applicable. Single seated means whatever we are familiar with so far, that this is the stem and this is the plug. So the fluid flows through this path. So this is the a single plug and single seat area is there. This is called single seated control valve. For double seated valve, this fluid flow can be divided through two parts, and two plug and seat area was there, so that the fluid can flow through these two. Why this arrangement is required? For single seated valve, this is more tightly fitted valve. That means since it has a single plug and single seat area, it can be fitted more tightly. But the problem is the thrust of fluid over this plug is more. But if the fluid flow can be divided by two paths, then the thrust on the plug will be less, comparatively less than the single seated valve. And if the thrust on the plug is more, then what will happen? In order to balance the upward thrust, the actuated diaphragm should be more, so that in order to balance the that force, so that means the size of the plug final control element will be larger compared to the double seated. So that is why this double seated valve concept arises. Single-seated valve has only one seat area. It has the advantage that it can more tightly close valve than the double-seated valve. But the disadvantage is that the thrust on the plug due to flowing fluid is very high. So large diaphragm area of the actuator is required to produce a force greater than that thrust. But for double-seated plug, the fluid enters the valve body between two seats and is thus divided into two streams. So the surface area of the upper and lower plug are almost equal, and the thrust force due to differential pressure existing across the plug in the process fluid is almost equal and opposite for two plugs. And so the net force which should be applied to the plug stem is negligibly small. So the area of the actuator required to produce a force greater than the net thrust force may be very small. That is the major difference of single-seated plug and double-seated plug. So the valve may be accurately positioned without the help of positioner. So in last class we have discussed that the purpose of using the valve positioner. So since the valve cannot position in a single attempt, so positioner helps to position the valve more properly, that is the rightly fitted to the seat area. But if the plug is a double seated, due to the division of fluid flow and the pressure existing, differential pressure existing across the plug in the process fluid for both the plugs equal and opposite, so the net force should be applied to the plug stem is negligibly small. So the area of the actuator requirement to produce a force greater than the net thrust force may be very small, which is significantly large for single-seated valve. So the valve may be accurately positioned without the help of positioner. That is why double-seated valves are widely used in three-term control, that is for PID controller. Disadvantages of definitely it has a drawback, that as it has two seat area, so the force applied on the plug by the actuator is small. So the tight shut-off condition of the valve at low flow condition cannot be easily obtained. That means a leakage flow will exist for double-seated plug. Whereas for single-seated valve, the major advantage is it can more tightly fit the valve. That means it can more tightly close the valve than double-seated valve. Next is the different types of plug. Depending on type of plug, the classification of control valve are poppet type or quick opening type. This is poppet type, that is the name signifies that it is quick opening type. This is specially used for on-off controller, where the stem movement, stem is positioned for maximum and minimum opening. And V-port type and contour type, poppet type and other two types are V-port type and contour type. Contour type is the smooth contour type plug, the figure as we have seen in the last diagram. And V-port type is a notch type. This is these two types of plugs are used for three-term controllers. This is the notch type or V-port type. Its structure is like that. And contour type is the smooth plug, contour type. And Poppet type is the seat is like this, and this will fit exactly to the seat area. So this type of structure is called poppet type. This is single seated valve with poppet type. This is double seated valve with poppet type. This is V type or notch type, and this is contour type. Both these are single seated. Corresponding double seated may be there depending on application. Next is flow characteristics. Valve flow characteristics is very important feature that it describes how the flow rate changes with the movement of stem upliftment. So actually the purpose of final control element is to change the fluid flow rate depending on the stem movement. So the flow characteristics describes the flow rate changes with the movement of stem. The shape of the plug primarily decides the flow characteristics. However, the design of the control valve and its shapes requires further discussion. The flow characteristics of the valve is normally defined in terms of inherent characteristics and effective characteristics. Flow characteristics of a valve is defined in terms of inherent characteristics, or inherent characteristics means ideal characteristics that consist of that is the characteristics of the valve type itself. And effective characteristics means effectively when the valve is connected to the pipeline, its overall performance is decided by its effective characteristics. That is actually the performance of a valve used in a particular flow line. So inherent characteristics is the ideal flow characteristics of that particular valve used and is decided by the shape and size of the plug. And effective characteristics is the actual characteristics of valve, which depends on the performance of valve along with the path, that means where it is fitted in the pipeline, and the overall performance depending on type of fluid flow, because if the fluid is a smooth fluid flow, a thin fluid flow, and if the fluid flow is a thick fluid, then that will matter the flow rate. So first is inherent characteristics or ideal characteristics, that is obtained from Bernoulli's principle, that the control valve acts like an orifice, and the position of the plug decides the area of opening of the orifice. So flow rate through an orifice can be expressed in terms of the pressure difference of upstream and downstream. So the flow rate Q is proportional to the pressure head difference. So this is K1A, this is flow coefficient, this is area of control valve opening, and these are the pressure static pressure head of upstream and downstream. So the difference of these two. This is from Bernoulli's principle, the ideal characteristics. So the area of the control valve opening is again dependent on the stem position or or the lift. So if the upstream and downstream static pressure head are maintained constant, then the flow rate is a function of the position. So the pressure difference, that means the upstream and downstream pressure static head maintained at constant pressure, H1 H2 difference is constant. So the flow rate is a function of stem movement, that is stem position. So this is the function of stem position. Q is proportional to Fz. The shape of the plug decides how the flow rate changes with the stem movement or lift. So the characteristic Q versus Z is known as the inherent characteristics of the valve. So let define this M as the ratio of Q by Q max and X as Z by Z max, where Q max is the maximum flow rate when the valve is, maximum flow rate means when valve is at full open position, and Z max is the corresponding lift valve position. So the equation can be written as the M, that is the controller output. So M is proportional, or M is a function of X. X is the ratio of Z by Z max. So the controller output is the function of the stem movement. Now the valve sensitivity is defined as dm dx, or the slope of the curve M versus X. See, the valve sensitivity is the slope of the curve. That means dm dx. In this way, the control valves can be classified in terms of their M versus X characteristics. So initially, the flow rate is a function of Z, and then it is finally expressed as M function of X. So the valve sensitivity and valve characteristics are defined as M versus X curve, and three different types of characteristics are quick opening type, linear type, and equal percentage type. So it has to be kept in mind that all the characteristics are to be determined after maintaining constant pressure difference across the valve, because during this simplification we considered that the pressure head difference, the upstream and downstream static pressure head are somehow maintained at constant. So the relationship M function of X is derived with the consideration that the pressure head difference is maintained at a constant pressure. Now what is quick opening type, linear type, and equal percentage type characteristics? Name signifies its operation. Quick opening means it quickly responded. That means say for 30% opening of this is the lift and M versus X characteristics. So say for 30% stem lift, the fluid flow rate is almost 80%. So this is quickly functioning. Again, this is for on-off type control action, with the consideration that delta P is constant. The pressure difference between the upstream and downstream of the valve is constant. Linear type means when it is linearly responded. That means the steam flow, the response in terms of flow rate with the stem lift is linearly related, and equal percentage is equally changes the percentage. There is a small difference between this linear and equal percentage. What is that? I am trying to explain. First is quick opening type. This is generally found in on-off control valve, where about 90% of maximum flow is obtained for about 30% of stem movement, and it is found that below 90% flow, it is the characteristics is almost linearly related with the percentage lift of the valve stem. This is typically the characteristics of on-off type control valve. Linear characteristics where dm dx is 1. The flow rate is linearly related with the stem movement, so that for any stem position of the flow rate, for any stem position of the flow rate, generally V-port type valve has this type of characteristics, which is normally used for 3-term controllers, PID controllers. And equal percentage characteristics. This is the characteristics used in which percentage change in stem position produces an equal percentage change in flow. Percentage change in stem position produces an equal percentage change of flow. Then what is the difference with this linear characteristics? Say for valve having flow rate 60 liter per minute at 50% stem position, so that will have 60 plus 10% of 60. For valve having 60 liter per minute at 50% opening position, stem position, will have 60, that is the flow value, plus the 10% change of 60 for increase of 10%, that is from 50 to 60%, but this is the equal percentage change. When the stem position changes by 10%, that means the 50% opening to 60% stem position opening. The for equal percentage characteristic stem valve, the flow rate is 60, that was the initial value at 50% stem position, plus due to change of 10% stem position, the change in flow rate is 10% of 60. This is for equal percentage characteristics. But in case of linear valve, for linear valve, 60 is the 60 liter per minute was the flow rate for at 50%. For 60%, that will be 60 by 50 into 60, and that value is 72 liter per minute. Whereas for this is 66, 60 plus 10% of 60. So that is the 66 liter per minute. Whereas for equal percentage, the flow rate is more, that is 72 liter per minute. So this is the difference between linear characteristics and equal percentage characteristics. Mind that all these characteristics I am explaining here in terms of inherent characteristics or ideal characteristics. That means when this is considering with the valve only. For an equal percentage valve, the flow characteristics is mathematically expressed as dm dx equals to beta into x. But for linear characteristics, that was 1. dm dx is 1. Here this is equals to beta into x, where beta is the constant. That indicates that the slope of the flow characteristics is proportional to the present flow rate, justifying the term equal percentage. This flow characteristic is linear on a semi-log graph paper. The minimum flow rate m0, that is flow rate at x equals to 0, is never 0. See, this is the characteristics where the minimum for linear characteristic, it starts from 0 position, but for equal percentage it starts with a minimum value, that is constant value is called m0 here. So the minimum flow rate is never 0 for an equal percentage valve, and m can be expressed as m equals to m0 e to the power beta into x. Beta is the constant of this slope obtained from the slope dm dx. So this is the exponential relationship of the controller output, where the m0 is the initial minimum flow rate, even when the flow rate x equals to 0. that means stem position, this is the m0 is the minimum flow rate at stem position x equals to 0. So the problem is, for this type of valve, tight shut-off condition is not possible, since even at 0 position there is a leakage, there is a minimum flow rate. So even at extreme minimum position of the stem movement, there is a minimum flow exists. So as a result, at minimum position of the stem, there is a leakage. So for this type of valve, a term rangeability is defined as maximum controllable flow to the minimum controllable flow. So the rangeability R, the flow rate of at any stem position for this kind of equal percentage valve is defined as Q is equals to Q minimum R to the power S by S max. R is the rangeability. Next is effective characteristics. So far we have discussed the characteristics as ideal characteristics of a valve without consideration of the typical process. That means where the valve is present, that the ambience, the pipeline, the fittings, the fluid flow type, flowing fluid type, without considering all these features. So that is purely ideal characteristics, and effective characteristics or real characteristics is the ideal characteristics of a control valve is decided by the shape of the plug, and the pressure drop across the valve is assumed to be held to constant. But the control valve is installed in conjunction with other equipment, say the heat exchanger, pipeline, orifice, pump, whatever be the devices connected in the flow path. The elements have their own flow versus pressure characteristics, and that will cause an additional frictional loss in the system, and the effective characteristics of the valve will be different from the ideal one. So let's consider a control valve connected with a pipeline of length L in between two tanks, and we consider the tanks are large enough so that the heads of the two tanks can be assumed to be constant. That means the initial criteria, the pressure difference across the valve must be equals to constant. We also assume that the ideal characteristics of the control valve is linear. Why we are considering the linear valve? Because the linear valve is the most required type of valve, because even, at the tight shut-off conditions can be achieved for low flow. So linear characteristics is always desirable. So the ideal characteristics of the valve is considered as linear. That means the K1A is equals to Kz, where K is the constant and Z the stem position. So this is the two systems connected by a pipeline, and the plug is there. So the pressure head difference H0 and H2 difference is considered as a constant. The length of this side is L. Now the pipeline will experience some head loss that is again dependent on the velocity of the fluid. So this is the real system problem, that it will experience some head loss due to the velocity of fluid. So that should be considered, or that will affect the flow characteristics. Now consider the expression. The head loss delta HL will affect the overall flow rate Q, and this can be rewritten as Q is equals to, just consider the Bernoulli's principle. From Bernoulli's principle, the Q is proportional to or equals to some constant root of 2G, the pressure head difference, H0 minus H2, and since the delta HL is the head loss of due to fluid velocity, so that is another loss, not only H0 minus H2 but minus delta HL into Z. So the head loss can be calculated from this relationship, that delta HL is F, that is the frictional coefficient, L by D. L is the length of the pipe as shown in figure, D is the dia, inside dia of the pipeline, and V is the velocity. So V square by 2G. So further, the velocity of the fluid, this V can be related to the fluid flow Q as Q by pi by 4 D square, that is the area. So from this expression delta HL, and if we put V over there, then delta HL is like this, and putting that to Q value, we will get Q is function of this, where alpha is a constant as FL K square. All are constant values. So it can be concluded that Q is, see, now the Q is, here is the Z, but there is a square root, at denominator there is a square root of Z square, under square root there is a Z square. So the characteristics is no more linear to the stem lift. That is the effect of effective characteristics. Initially the valve characteristics was considered as linear valve characteristics, but after consideration with the real system, that means the pipeline, the head loss due to fluid velocity, and we are getting that Q, that is the flow rate, is no more linearly related with Z, but there is a non-linearity with this. And the characteristics, how the characteristics will be changed, that is, if we plot the response of Q versus Z from here, then the flow characteristics, the ideal characteristics was that much linear, and now the response of this Q is like this, since there is a at denominator there is a Z square factor. So as the pipe diameter decreases, see, this is the there is a coefficient, a constant value alpha, which is inversely related with D5. So as the pipe dia decreases, with the decreasing pipe diameter, the curve will be more non-linear, and it tends towards the lower portion. So the Q is no longer linearly proportional to the stem lift, though the ideal characteristics of the valve is linear. this non-linearity of the characteristic is dependent on the diameter of the pipeline D. That is, smaller the pipe diameter, larger the value of alpha, and more is the non-linearity. Just get cleared about this concept, that even the ideal characteristics was linear, but due to the effect of real systems, due to other attachments in the path, fluid flow path, the non-linearity, the fluid flow characteristics becomes non-linear, and the non-linearity of the effective valve characteristics is like that. With the decreasing pipe diameter, it will be more, the response will look like this. So this is the ideal characteristics, and the actual characteristics becomes like this characteristics. Now the non-linearity introduced in the effective characteristic can be reduced by increasing the pipe diameter, thus reducing the head loss and increasing the pressure of the source. So these are the two methods by which the non-linearity can be reduced. Increasing the pipe diameter, that is the D value increases, means the alpha value becomes smaller, thus reducing the head loss and increasing the pressure of the source H0, and decreasing the pressure at the termination, that is H2. And initially we have considered that H0 difference H2 was constant. So the effective characteristics of the control valve are in terms of absolute flow rate Q versus Z. Before that, that was M versus X, but this is flow versus, that means Q versus Z. Initially it was defined as Q versus Z. Just rewind the expression for the characteristics. The characteristics was initially defined as Q versus Z. From that it was simplified as M versus X, and effective characteristics is always Q versus Z. That is flow rate with the stem movement. The effective characteristics will deviate. Effective characteristics M versus X will deviate upward. The previous one was Q versus Z, flow versus lift. So if we draw the M versus X, that will deviate upward. The ideal characteristics, which was linearly related, that just think about this one. The ideal characteristics is looks like this. That was the ideal characteristics, and the real characteristics is bend downward direction. So if from this we plot M versus X, then what will happen? This ideal characteristics will deviate upward direction. This M versus X will deviate upward. This is the effective characteristics, which was initially linear for ideal characteristic. So if we consider the quick opening type valve, quick opening type valve was like this type of characteristics was there for quick opening type. So if the ideal characteristics was quick opening type, then with the upliftment, the effective characteristics become more linear compared to the ideal characteristics linear valve. linear characteristics. So the linear valves are recommended when pressure drop across the control valve is expected to be fairly constant. On the other hand, equal percentage valves are recommended when the pressure drop across the control valve would not be constant due to the presence of series resistance in the line. As the line loss increases, the effective characteristics of the equal percentage valve will move closer to the linear relationship, that is in M versus X characteristics. The performance of the control valve is sometimes defined by the turn down or turn down coefficient or turn down factor, or that is the ratio of normal maximum flow to maximum controllable flow. So this is a very common question, why equal percentage valve are recommended than linear valve for where the pressure is not constant. Pressure difference is not maintained at the constant value. So that will be the that is the reason why this kind of equal percentage valve is more advantageous than the linear valve. Next is control valve sizing. Control valve sizing is another important aspect of for valve designing, because due to change of stem movement, the positioning of plug to the seat area is very much important. So valve sizing means sizing of all the parts of control valve. So this is very important aspect, and proper size of the control valve is selected so that the control of flow over a wide range is possible. The pressure drop, flow and specific gravity determines the selection of control valve. In ideal condition, Q is K root delta P by G, where G is the specific gravity, A is the opening area of the control valve, and K proportionality constant, delta P is the pressure difference. And there are other characteristics such as the type of fluid, that is maybe gas or liquid, critical flow conditions for gases and vapor, viscosity of the liquid, all these factors influences the valve sizing. To select a valve, the flow condition has to be such that the process characteristics and the valve characteristic must match with each other, so that nonlinear of the overall control loop may be eliminated. That is another aspect of valve selection, that to select a valve, the flow condition has to be such that the process characteristics and the valve characteristic must match with each other. Process characteristics and valve characteristics. Otherwise, if the process characteristics and valve characteristics mismatches, then non-linearity will be more. Say, for if the control valve is oversized, then the minimum controllable flow is too large. Oversized means the valve sizing is more and the minimum controllable flow is too large, and if it is undersized, then the required maximum flow may not be provided by the valve. Hence, the proper sizing of the control valve is always necessary, and it is selected and designed by correcting the ideal discharge constant K. So, in order to sizing a control valve by this method, a factor called flow coefficient factor CV or valve coefficient factor, that is Q is proportional to delta P, and this is Q is equals to CV root over of delta P by G. This is called valve coefficient factor. this CV factor is defined, this is as per definition, that number of US gallon of water flowing per minute at 60 degree Fahrenheit, this is standard definition, through a fully open control valve under pressure drop of 1 psi. Now for liquid, steam and gas, the correction factors, that is the K dash, due to correction factors due to temperature, specific volume and specific gravity are considered, and the flow equations are modified as, for liquid these are the typical values for the corrections. So CV is the valve coefficient, delta P is the pressure drop across the valve in kilonewton per meter square, P is the inlet pressure at kilonewton per meter square, G specific gravity, V specific volume of steam, and T temperature in centigrade, and 1 US gallon means 3.8 liter. This is from standard definition. Now there are certain steps of designing a proper size of the control valve. So all these steps are very much important. Actually control valve sizing is a very important aspect for design consideration. So there are a number of features and methodologies for designing. This is just a brief overview of certain steps, that these steps must be maintained to for designing a proper sized control valve. For a particular process under control, first determine maximum value of the flow rate required to maintain the control variation under any condition of the process operation. This gives the normal maximum flow rate. The value of flow rate that will require for most of the time, this gives the normal flow rate, and minimum flow rate. That means maximum, minimum and normal flow rate are to be determined. Next is select the maximum flow rate which the control valve is to provide. This is generally selected 1.4 times of normal maximum flow rate. Next is select the type and style of the control valve for best operation. And for this selection, the rangeability of the valve has to be selected so that the minimum controllable flow rate is generally smaller than the normal minimum flow rate. Next is calculate the pressure difference at the control valve at the maximum flow rate considering a pressure loss. So all these are the steps, and all these steps should be maintained properly in order to get proper sized valve. Next is determine the control valve size from the manufacturer monograph chart by calculating the value of flow equation of the control valve, that is the standard flow equation. Now if the fluid viscosity is high or the velocity of fluid is exceptionally low, then the size coefficient will be low, and manufacturer should be asked to determine for that condition of the process. That means this is for the typical operations. If the fluid is a high viscous fluid or the velocity of the fluid is exceptionally low. Next is the characteristics coefficient, defined the difference in pressure where CV is fully opened to the difference in pressure when CV is fully closed. Alpha, if alpha is less than 0.1 or alpha is less than 1/2500 to Q by Q minimum square. Q is the normal flow rate and Q minimum is the normal minimum flow rate. Then the control valve will require to operate at less than 2% of the total lift. In this case, the control valve should have a powerful actuator, and accurate valve seat and plug or the difference pressure head should be increased by selecting larger pump, larger line size, and minimizing the line loss. So these 6 basic steps are to be followed for designing proper sized valve. The for valve sizing, you may consult the book of LeapTap, that is the most where it is defined clearly about the control valve sizing and how the in order to what are the steps and how to maintain the process so that the how to maintain the steps so that the proper sized valve can be designed. So that's all about control valve as per your syllabus. In handbook there are many other issues addressed. So I think this much is enough for your content. Thank you.